So last time we saw a toy example, the cycle. Now I want to move to another toy example. So second toy model, which is a simple random walk. On the n cube. Okay, so what is that? The state space is just the hypercube, so the n-dimensional Boolean hypercube. And then the transition matrix is as follows. So whenever your clock rings, most of the time you do nothing, and so the only possible transitions is when you flip a coordinate, right? And you do this uniformly. So when your clock rings, you just pick a coordinate uniformly at random and you change the sign. So it's 1 over n if x and y differ at exactly one place and 0 else. Okay. So this notation means that the x and y differ by exactly a coordinate. Okay, so just a picture for n equals 3. Right, so this is this graph, and you move from whenever the clock rings, you move to a uniformly chosen neighbor in this graph. Okay, so again, it's a very symmetric model. So every state in the state space plays the same role. So by symmetry, you know that pi is uniform on the state space, and you also don't really need to care about the starting point. So I'm going to start from the identity without loss of generality. Okay. And again, this model is so simple that you can do computations exactly. So the nice property with this model, that's the point. One of the nice things when you work in continuous time is that you see, I told you, whenever the clock rings, you choose a coordinate uniformly at random and you flip it. But that's exactly the same as saying that each coordinate independently is flipped at a rate which is 1 over n. Okay. So the nice thing is that the coordinates evolve independently of each other. So you have this nice product form. So if you want to compute the probability that at time t you see a particular state, it's just a product. So all the coordinates are IID, and now you just need to compute the chance that a particular coordinate is +1 or -1. So it starts at +1, and then it is flipped at rate 1 over n. Okay. So the only thing you need to compute is the probability that a Poisson variable with mean t over n is even or odd. Right? And so what you get is this when you do the computations. Okay. Okay, and you see when t tends to infinity, this disappears and you get the uniform measure. Okay, so the question is how close are you from the uniform measure, or how far are you from the uniform measure when t is anything. Okay. Maybe just to normalize this. So if you divide this by the stationary measure, it's the same as just removing these two. And we'll use it. Okay, so this is completely explicit, so you can compute the total variation distance to equilibrium now. Okay, so remember one of the many formulas we have seen was this. The sum over all states. Okay, and you had this minus probability that xt is equal to x plus. So the positive part. And this I'm going to write it as follows. So it's 1 minus this ratio here. Okay? But this is sum of pi of x times something, so it's really an expectation, right? There is a positive part. So it's really an expectation, so I'm going to write it like that. It's expectation of positive part of 1 minus this. And now this small x becomes a random coordinate, which is chosen according to pi. So there is no 2. Okay, so let me introduce this quantity. So you can rewrite this like that. So it's expectation of positive part of 1 minus exponential of WT plus where WT is just the log of this quantity. Okay, so it's a sum of IID variables, right? Those xi here are just IID uniform on -1, 1. So it's a very simple variable. And you need to understand this expectation to know the total variation distance, okay? So now we want to take n to infinity and try to see what's the right choice of t so that this quantity becomes small. Okay, so let me do a Taylor expansion. So now, if t depends on n and becomes large compared to n, and n becomes large as well, so in this regime, you can do Taylor in this sum. So you Taylor the log, so you get this. And then there is the second term, which is xi squared, but xi squared is just 1. And then plus some correction. Okay, so this is really times this. And then there is a 2. Minus n over root 2 times this. And then plus little o of this. Okay, but now n is large. Those are IID variables. So this is roughly square root of n times the standard Gaussian by the CLT. Okay, so now, in particular, if you look at this regime, if you take t, which is like a constant times n log n, right? So alpha is just a constant, and then you look at t of this form, then you see that there are two different behaviors. So if alpha is less than 1/4, then this term here will tend to plus infinity. So this one as well, square root of n times this will tend to plus infinity, but this is much larger. It's the square of this one. So this one takes all of it, and you get minus infinity. So in this regime, your the variable becomes in probability minus infinity, and when you plug this here, you just get 1. Okay, just by dominated convergence. Everything depends on n, right? And when you look at this t, which is t of n, you get just 1. Okay. On the other hand, if you look at alpha, which is larger than 1/4, then this term now tends to 0, right? This term as well, square root of n times this tends to 0, and so everything tends to 0 in probability. And so when you plug this here and use dominated convergence, you get that the total variation distance at your particular time tends to 0. Okay. So what's the picture that you get? So that's what I announced yesterday without a proof, but now you have a complete proof. So if you look at the graph of your distance to equilibrium as a function of time, it converges as n tends to infinity, just like in the case of the cycle. You see a limiting profile when you look at the correct time scale. Maybe you can call this t. But this depends on now instead of having a nice smooth function, you get a step function. It's 0 if t is less than 1/4. It's 1 if t is less than 1/4, and it's 0 always. Okay. So what it means again in the limit is that your convergence to equilibrium is very abrupt. So you run your dynamics, nothing's happened until this particular time, n log n over 4. And at that time, your distance drops from close to 1 to close to 0. Okay. Okay, so this is a phase transition in the way in which your process converges to equilibrium, and this phase transition is called a cutoff. So that's our first example of a cutoff. Okay. So now you could try to refine a bit this computation. Everything is so simple in this model that you can compute many things. So in particular, you would like to zoom here. You know that the transition occurs very abruptly around this point, but you could try to zoom and see how to zoom around this point n log n over 4 to see the transition from 1 to 0 occurring. And you see from this computation that in order to see something between 0 and 1, you just need this WT to be between minus infinity and 0, to be some constant. And you see that the right scaling to do that is to choose, instead of this, you choose n over 4, and now plus a correction which is like n times the constant. And then everything here, this WT will converge to, instead you will have, in this regime, your WT will converge in the distribution as n tends to infinity to just exponential minus 2s times a Gaussian, and then minus this. And then there's a 2. Okay, and you can plug this here, use dominated convergence, and you get a non-trivial, an explicit non-trivial value for your distance to equilibrium. So this tells you that on this graph, if you want to really see the transition, you need to zoom at distance n around this point, and then you will see a smooth profile in the limit given by this. Yes, exactly. Okay, so we won't go into this refinement, but here you can really say something very precise about what happens inside the critical window, if you wish. Okay, but for us, this is the only, the main point is this. Okay, so maybe in terms of mixing times, just to translate in terms of mixing times. Once you understand the distance to equilibrium, the mixing time is just the inverse of this function. So what's the time at which this function reaches precision epsilon? It's just 1/4 n log n independently of epsilon. Okay, so that's very different from the cycle. In the case of the cycle, you had instead of n log n, it was n squared, but this is not very important. The constant in front was really depending on your precision epsilon. Now this does not depend on epsilon, and it's the same as saying that you see this step function in the limit. Okay, so now I can define this cutoff phenomenon in a more general way, more formal way. This was just an example. No, so this function, this total variation distance, remember it was defined as in terms of the semigroup Pt. Pt is a continuous function of t. So this function dTv of t in general, is continuous for a finite state space Markov chain. So you cannot see a phase transition, right? It's a continuous function. You cannot see a step function like that. It's only in the limit. That's a general thing about phase transition. You never see them in the finite world. You need to take it. Those phase transitions, they occur in the limit where a parameter tends to infinity. Okay, so now I can start my my second lecture, which is really the cutoff. Okay, so let me give you the general definition and the main question. Okay, so the definition was introduced by Aldous and Diaconis. It was 14 years ago, in the 80s. So remember that it's not something that works for a fixed state space Markov chain. You have to consider a model where there is a size parameter n that tends to infinity. So we are going to say that a model exhibits cutoff if the mixing time of your model does not depend on epsilon in the limit. Okay. Okay. So, the correct way to interpret this is by looking at this picture here. You see when you're saying that asymptotically this quantity and this one becomes the same, right? Which means that your function becomes more and more like a step function, like that. Okay, so it's really the same as saying this. So it's totally equivalent, this definition, to saying that you have something like that, where instead of having this, you have constant times t, some scale function, and then you have this if alpha is less than 1, and this is alpha if alpha is more than 1. So it's the same thing, saying this or saying this. Okay. So we saw one example of a model for which you don't have cutoff. So that was random walk on the cycle, and we saw one where you have cutoff. Okay. So let me tell you a bit of history behind this this definition. So this was discovered on card shuffling. Okay, so there is a nice story behind that. So, Percy Diaconis was a professional magician before being a mathematician, and so he was playing with cards a lot. And he realized that when you shuffle a deck of cards, in the usual way, so you take your deck, you split it into two parts, and you recombine them at random. Right? So that's the usual shuffling mechanism that you would do. And you can ask the question of mixing time is how many times you need to repeat this shuffling procedure so that your deck is close to being uniformly distributed. Right? And he realized that there is a cutoff for this. Right? Cutoff in the sense that if you have a deck of n cards and n tends to infinity, this phenomenon occurs. Okay? So the point at which it occurs as a function of n is like log n 3/2 of log n base 2. Okay, and when you compute this for n equals 52, you get 8, something like 8. Okay, so it means that if you shuffle a deck of cards slightly less than 8 times, then you are actually very close to total variation distance being 1, which means that there is an event that is almost that is very likely to be realized for your deck. But if your deck was really at equilibrium, really uniformly distributed, the probability to see this event would be close to 0. Right? So he started betting on this property because he realized that in casinos, people would shuffle the deck like 5 or 6 times instead of 8. And then he won a lot of money. until he got kicked out from this casino, because you are not allowed to, it's not cheating, it's just thinking, but you are not allowed to do that. And not only he was kicked out of this casino, but he was blacklisted from all casinos over the US. But the story is not over, so he continued to gain money out of this idea, because then he got recruited by as a consulting expert by a company that actually constructs shuffling machines, right? And then he explained to those people that the deck should be shuffled at least 8 times, and not much more actually, because then it's useless to continue. So it's really something, I'm mentioning this just to motivate you. So cutoff can get you money, right, first. And second, it's something that we are thinking about asymptotics because we like that in mathematics, but it's really something that actually occurs concretely when n equals 52. So it's not a mathematical curiosity, if you wish. It's really something that happens in the real world. Okay, so this was the main context where cutoff was discovered. But after that, cutoff was observed in many other contexts, right? So one of them where you see a lot of examples of cutoff are random walks on groups. Okay, so maybe I should give references. So there are hundreds of examples now of cutoff, so I cannot cite everyone, but what I'm going to do is in each of those, I'm going to list a few categories where where cutoff have been proved, and for each of them I will give you one reference. So your job will be to look at all the references that are cited by the paper to get a proper vision of the state of the art. So maybe the paper that formalizes the example of card shuffling that I just mentioned is a paper by a very nice paper by Bayer and Diaconis. It was Annals of Applied Probability in 92. Okay, but again, it's just one example. There are many card shuffling schemes, and for some of them, cutoff has been proved. Just look at this one and all the papers that are cited or that cite this one, and then you will get a proper. Okay, so random walks on groups. Right, you take your favorite finite group and you make a random walk on it by just drawing independent elements from a subset of your group and then multiplying them together. So this is a Markov chain. And if you multiply sufficiently many terms in your product, what you will get is something that is close to uniform. So that's actually a way to generate a close to uniform element of a very complicated group. And that's a way that is actually used. In fact, if you think about it, card shuffling is exactly that. It's the group is the group of permutation, but that's what you do. Okay, so there are people in group theory that study groups through the behavior of random walks. So it's a very natural thing to do. So here the reference I want to highlight is one by there are many again. One by Berestiki and Sengul. I think it's PTRF 19. I like it because it's one of the very first use of curvature in proof of cutoff, and that's something that, as you will see, that is very, very important. Okay, so another context that maybe some of you in the audience are more interested in is Monte Carlo Markov chain. So again, I will try to say more about this later, but the game here is that you have a complicated target distribution pi, and in order to get samples from this distribution, you run a Markov chain that has pi as a stationary measure. And of course, there it's crucial to understand the speed at which you converge to pi. And for some of those models, you do get a cutoff. So here, the best paper I can think of is one by Lubetsky and Sly. It's Invenciones 13, where they prove cutoff for the Glauber dynamics for the Ising model on grids. So it's a fantastic paper that really uses key properties of the very fine properties of the Ising model on lattices, and it's a wonderful paper. But again, it's just one example. There are many many other examples of cutoff in this category. Maybe interacting particles. So you take your favorite model of interacting particles. So mine personally is the exclusion process on a large graph. And then you can ask whether the dynamics exhibit cutoff. And this has been done there are many models of interacting particles. And for some of them, if they are simple enough, say mean field or on the line, then you can compute things and prove cutoff. And, the most famous paper in that direction is one by Hubert-Lacroix. So it's Annals of Probability 15, where he proves cutoff for the exclusion, simple symmetric exclusion on a segment of length n. Okay. And finally, this cutoff phenomenon, so people believe that it's something that is universal, so they try to look at what happens when you take a sequence of, when you take a model at random, right? So you pick your transition matrices at random from a certain distribution, and then you ask whether there is this cutoff phenomenon. Those are random, but in probabilities. And so one particular example of this is when you take simple random walk on a graph, but the graph is random. Right? So do you get cutoff? Is cutoff something that is generic? And the answer is yes. And there is a very nice paper by, okay, maybe I should say. So random walks on random graphs. So there are infinitely many models of random graphs. For each of them, you can try to see whether there is cutoff for random walk. So there have been a huge number of works on this. But the one I want to emphasize here is the one by Jonathan Hermond, Alan Sly, and Perla Suzy. It's Annals of Probability 22. Okay. Okay, so you see from this list that cutoff is something that happens in many different contexts. So it seems like something we understand well now. And again, this is just a very personal list of references, but the good news is that you have more than 100 examples. Okay. Also, I want to stick to finite state spaces, but you could add to this list diffusions on manifolds, and also there you have examples. Okay, so the bad news. But if you look at the proof of those results, it's very disappointing in the sense that it's model specific. So there is no general theory. It's even worse than that. If you look at the proof, it's just brute force, essentially brute force computation. Okay, think of the example we just saw. Our only example so far is this random walk on the hypercube. The way we prove cutoff is by computing exactly the distribution at any time t. You had this nice product form, and from that you could extract explicit asymptotic. So we did just brute force computations for the hypercube. And in the end, you realize that there is cutoff by computation, but there are two bad things about this. The first thing is that it's an approach that is very fragile in the sense that it will only work for models where you can compute everything. So there are very little of them. And the second bad thing is that for those models, you compute everything, you realize that there is a phase transition, but you really did not understand why. Right? So from this computation proof, it's not at all clear why the hypercube exhibits cutoff and the cycle doesn't. It's just you do computations and then you just realize that there is a cutoff, but it doesn't really give you any understanding of the phase transition, of the real reason why there is a phase transition. Okay. Okay, so maybe I should explain to you why this is so why this method is so fragile and so difficult. Right? So if you see the references there, they are quite good probability journals. And the reason is that it's generally very difficult to establish cutoff. It's something that requires a lot of detailed computations about your model. Right? Think of what we did for the cycle was the local limit theorem. Right? Essentially, to understand cutoff, you need to understand your model so well that you can almost explicitate the distribution at any time, right? So what you would need is the equivalent of the local limit theorem, but for all of those models. So it's something that is not easy to do. Okay. So how do you prove cutoff in those examples? Well, you open your favorite book on mixing time. And the theory of mixing time is just a bunch of, it's a collection of results that allow you to bound your mixing time, upper and lower bounds, right, in terms of simple quantity of your Markov chain. Right? So you get bonds like that. Okay, and it's a very rich theory. There are many ways to obtain bonds. So you can use coupling, right? Try to couple trajectories so that they meet quickly, and then if you can estimate the time at which they meet, you will get upper bounds on your mixing time. You can also try to apply your favorite functional inequalities, and we'll see how this works, to get bounds. You can use the eigenvalue and eigenvector structure of your transition matrix to get lower and upper bounds, if you can compute those things. There is also a geometric perspective on mixing times where you can use this idea of curvature to get bounds. So it's a very rich theory. I really recommend reading the book by Perez and Wilmer on this. Perez and Levine, sorry, on this. Okay, so now you are interested in your particular model. So remember that in a model, everything depends on n. You apply one of those bounds to get an upper and a lower bound. And in this business, if your model is simple enough, you can hope for this lower bound and this upper bound to be good enough so that they have the same order of magnitude. And then you are happy because you can claim that your mixing time is like n squared, constant times n squared, or constant time n log n. And that's already something that is very difficult to achieve in real-world models. Right? But this is far from enough if you want to understand the cutoff phenomenon. Right? If you want to understand the cutoff phenomenon, not only you need this to have the right order, the same order of magnitude as this, but you really need the prefactor in front to be the same. Right? What you need is the bonds that are accurate enough so that this tends to 1 as n tends to infinity. You really need to know the constant because it's all about the constant. Right? You see in my definition, you really care about the factors that you have here. Right? So you need bonds that are so precise that the prefactor is the same in front of both. And that's the reason why it's limited to, a small hundred of examples and not all models. Okay? So actually, Aldous and Diaconis realized that this was problematic. They immediately sort of conjectured that cutoff should be something universal. But they complained that the only cases where they could prove it was by brute force computations. And so they asked the following questions. And that will be the main question for the entire course. But again, it all dates back to Aldous and Diaconis. So the question is, can we get a proper theory of cutoff? So can we predict the cutoff on any model without having to do this? To compute the mixing time up to this prefactor precision. Right? So 1 plus little o of 1 precision. Okay, and that's a question. So it was 40 years ago that it was raised, and it's still open in generality. So it's still open, but very recently there was progress on this, and the goal of the course will be to present you this progress. It's very recent in the sense that when I received the invitation for this Saint-Flour lecture, I still didn't have an answer to this, and now there is an answer, but a partial answer in the sense that it works for half of the models. Only models where you have non-negative curvature, as you will see. For them, we start to have a theory of cutoff, but apart from that, it's still open. Okay. Okay, so maybe, before entering the details of this, why should we expect anything nice, right? Why is this reasonable? Okay. So let me spend some time describing an analogy, an interesting analogy. So consider another well-known phase transition in probability, nothing to do with Markov chain, it's concentration of measure. Concentration of measure is a phase transition. So let's keep things simple and just look at a sequence of random variables, say real valued or even non-negative, to keep things simple. So Zn. You say that it concentrates if there is a deterministic quantity, say Tn, such that you have this convergence in probability. Right? So Zn is random. Zn is random, but in the limit, it behaves more or less like a constant. Right? So for some deterministic sequence Tn. And of course, you can, if this is true, you can always take Tn to be the median of your random variable, and in many cases, the median is the same as the mean. Right? So in many interesting cases, this is just the expectation of Zn. Okay, so that's just a definition. Now there is a way to formulate this in terms of a phase transition for a function. Right, so let's plot a let's look at this function fn of t, which is just the probability. It's the tail distribution function of your variable. And so saying that you have this concentration of measure phenomenon is the same as saying that so this is 1, this is 0, fn of t is decreasing from 1 to 0. And what you are saying is that the transition becomes, the graph of this becomes more and more like a step function around this Ti. So it's exactly, I mean, at least at a formal level, it's exactly the same as this cutoff phenomenon. Right? If you replace this tail distribution function by your total variation distance to equilibrium, then this definition of concentration of measure is the same as the cutoff. Okay? Okay, so why am I saying this? Because, in concentration of measure theory, as you know, there are many tools now to predict that a sequence of variables will exhibit concentration in this sense, right? Without having to explicitate this tail distribution function. In fact, there are results that tell you that Zn will be concentrated around a certain quantity without even having to compute that quantity. Right? So, for example, any Zn which you can write as a function of many independent variables, as long as it does not depend too much on each of them individually, will be concentrated. And you don't need to compute expectation to do that. Right? So that's what this question is asking, but for the cutoff phenomenon. Right? So can we have a theory that allows you to predict cutoff without having to compute everything? Okay. Right, so if you transpose the situation about Markov chains here, what it would mean is that our only way to prove concentration is to actually explicitate the law of your random variable and check indeed by computation that you see this step function in the limit. Right? That's not at all what we do in concentration of measure. So do the same for Markov chain. So that's the main open problem for this lecture. There is another analogy. There are many phase transitions in probability. Another one is percolation. Take your favorite maybe monotone property of a graph and try to see, do percolation on your graph and try to see at which point, at which parameter p, your property becomes satisfied. Right? So this is also something that is monotone. So you can phrase it in this way, right? And so percolation is an example like that. And of course, in percolation, we have now many tools to understand that there is a phase transition on your favorite graph without having to know the critical threshold for percolation. So same thing here. Same question for Markov chains. Okay. Okay, so there has been a famous attempt to solve this question a decade ago. And I want to discuss this because it will play an important role. Oh. So this is a famous atom to solve this question of Aldous and Diaconis. So there was a workshop 20 years ago in AIM in the US about mixing times, and all the experts in the field were there. So of course David Aldous and Percy Diaconis, but also Yuval Perez, and so he proposed the following conjecture as an answer to this. So it's Yuval Perez in this AIM workshop in 2004. So what he says is that you have cutoff if and only if a certain criterion is satisfied. And this criterion is called the product condition, and it's this. So remember, in a Markov chain, you have those two time scales, convergence to equilibrium from far away, and convergence to equilibrium when you are already close to equilibrium. And you want this to tend to plus infinity. By the way, there is a huge mistake in the note. This is 1 in the lecture note. It should not be 1. It's really plus infinity. Okay, so there are several comments I want to make about this condition. So maybe first, I'm not indicating the epsilon here. Remember that when I don't put it, it means 1 over 2e, but in fact, we don't care, right? Because this does not really see the prefactors in front, and when you change epsilon, you just change the prefactor. So you don't really need to care about the precision. Okay. The second comment is that it's called the product condition, and there is no product here. Right? But remember that Tyrrell is 1 over the spectral gap. And then you'll see the condition is gap times T mix is plus infinity. So that's where the name comes from. Okay, so there are nice things about this conjecture. So the first thing is that this would really be an answer to this problem, right? In the sense that it's an effective criterion. Okay, so what do I mean by effective? Right? In order to determine whether this is true or not, you don't need to compute prefactors. You don't really care about 1 plus little or 1. It's just order of magnitude. So this is easy. Right? So even more than that, right? You just need a rough lower bound on the mixing time. And lower bound on the mixing times are easy to get, much easier than upper bound. Right? Just because total variation is the maximum over all possible events. And so getting a bound on this is hard. Whereas guessing what will be the bad event is generally easy. So you get the lower bound very easily. The hard thing is to convince people that your bad event is actually the right one. So this is much easier to get a lower bound on the mixing time. And this one is just 1 over the spectral gap. The spectral gap is a quantity that we understand very well in Markov chains. You have many tools to estimate it. You don't need to compute eigenvalues. There are variational characterization. You have Chigger inequalities. You have many tools to compute this. So my point is that for many interesting models like Monte Carlo Markov chain, take your favorite Glauber dynamics for de-Ising model on any sequence of graph. We know precisely as a function of the temperature, we know the regime in which this condition will be satisfied and the regime where it will not be. Okay? So this is really easy to determine, and it would be amazing to get such a simple criterion for cutoff. Okay? So the other nice thing is that this works on our toy models. Okay, so I told you, simple random walk on the cube and on the cycle, at a formal level, it's the same thing. Both are random walk on abelian groups, particular abelian groups. We'll see that later. Right? One exhibits cutoff, the other one doesn't. So what's the explanation? What is so different between the two models? And one thing where they differ is this product condition. So I told you yesterday that for the cycle, those two times were both n squared. Right? So the same order of magnitude for the mixing time and the relaxation time, and therefore the product condition is not satisfied. Now for the hypercube, this we saw is n log n, and you can compute everything. You can diagonalize the matrix very easily for the hypercube. It's a product thing, and the relaxation time is order n only. Right? So you have n log n and n, so this diverges. So that's a way in which those models are very different, and one satisfies the product condition, the other one doesn't. And that could be an explanation for the difference in terms of phase transition. Okay, another good news is that half of this conjecture has been proved. this is always true. Okay, so if you want a cutoff for a model, you really need this product condition to be satisfied. I'm going to prove this, it's one line. Okay. So in particular for the cycle, it's very easy to, without even computing things precisely, so you don't need the local limit theorem to prove this. It's very easy to see that this is not tending to plus infinity. And then you can conclude that there is no cutoff without having to go through delicate computations. Okay. So I'm going to prove this later. Or maybe let me do it now. It's very easy. So recall that you have a relation between those two. The mixing time from far away is always larger than this one. So you always have this. This we saw before. This is always larger than the relaxation time. And there is a dependency in epsilon, which is this. This is always true. And this comes from the fact that you have this sub-additive lemma where the limit is actually the infimum. This infimum gives you this inequality. Okay, now if there is cutoff, then your T-mix without any precision epsilon, so meaning epsilon is equal to 1 over 2e, will be the same, will be equivalent as n tends to infinity to T-mix of epsilon for any epsilon, right? So in particular, it will be larger than log of 1 over 2 epsilon, but for any epsilon. And now you get a problem because you can make epsilon as small as you want, so you can make this as large as you want compared to this. Right? So this is true for any epsilon. And so you get that the limit, the limit is larger than log of 1 over 2 epsilon for any epsilon. Okay, so that's a proof. Okay, so it looks very nice. So unfortunately, there is bad news. And the bad news is that in this AIM workshop where Yuval proposed this nice conjecture, David Aldous was sitting in the audience. And after an hour, apparently, so I checked with him and it's true. After an hour, he produced a counterexample. It's a very interesting one. It's quite complicated, but now I start to understand the reason, the idea behind it. So only now, but, so he got it in an hour. Okay, so of course it's counterexample to the opposite. By the way, this is nice, but this is not the answer to the question. We want to predict cutoff. So we are really interested in this direction. So unfortunately, there are counterexamples. But his counterexample is really cooked up so that it fails. So Yuval was not happy with that, and he said, no, that's not a reasonable counterexample. So he changed his conjecture, and he said, okay, here, no, for reasonable change. Okay, and unfortunately, this is still not true. So it's really, now the guy is crying. So counterexamples are everywhere. They are generic. So I'm going to explain that because it's important for what I want to do later. They are literally everywhere in Markov chains. So it's not like, if you restrict yourself to nice chains, then this will be true. No. Okay, so now this conjecture is still open in the sense that now what you need to do is find a reasonable meaning for this word here, so that this is true, and this is still wide open. Okay, so maybe let me explain to you why this is counterexamples are everywhere. There is a general theorem that I'm going to write down, which tells you that if you give me any model that satisfies this, so that satisfies cutoff, and so in particular, if it satisfies cutoff, it satisfies this, then I can modify it in a very tiny way, and I will get a counterexample to this. Okay. And the way I'm going to modify it is by doing a stupid rank 1 perturbation. So this is due to, it's a generic counterexample which is due to Igor Pak. And we'll learn a lot from this. It looks like a bad news, but we'll learn a lot from this. Okay, so the perturbation is very easy. You give me your favorite model, Txy, and I'm going to modify it as follows. So my new model is T tilde xy. And it's, you know, most of the time when my clock rings, I do what you used to do with your original model. I really do Txy. And this happens with probability very close to 1. So theta will be a parameter that is very small. But from time to time, I allow myself to do something else. And what I'm going to do is cheat and go directly to equilibrium in one step. Okay? Okay, so you might think that this is very different from the original model, but theta will tend to 0. Remember, it's a model, so everything depends on n. Right? Everything, there are n's everywhere. And we'll let theta n tend to 0 in the right way, and in a way that destroys cutoff. Okay? So here is the result I want to state, so maybe here. And we are going to prove it. So proposition. So start from a nice model that satisfies cutoff. And if we choose theta n carefully, so the way I'm going to choose it, I want it to be small, but not too small. I want it to be much smaller than 1 over the relaxation time of your original model, so Tyrrell of n, but much larger than 1 over the mixing time. So it goes to 0, but not too fast. By the way, this is always possible because there is room between Tmix and Tyrrell, just because, you know, if you have cutoff, you must have this product condition. So you have a lot of room between those two parts. You can always stick a theta n in between. Okay. Okay, then your modified model, so this Tn tilde, satisfies the product condition. So PC is this is PC, product condition. So your modified model satisfies PC, but no cutoff. It's completely destroyed. In fact, in the limit, you see a nice exponential form. Right? Your function will look like really like an exponential in the limit. So completely destroy cutoff. Okay, so before I prove this, I really want to insist on several interesting aspects of this counterexample. Okay, it's a transformation that preserves a lot of things about your model. Right? So if you start from a model that belongs to a certain class of nice Markov chains, say for example simple random walk on abelian groups. We'll define this precisely, but you know you take your favorite group and you add IID element in your group. That's a random walk on an abelian group. It's as nice as it can be. You can do Fourier analysis. Everything is almost explicit. If you do this transformation here, what you get is another random walk on the same abelian group. So it means that you will have a counterexample to Yuval's conjecture, even in this simple class of random walks on abelian groups. And you can replace random walk on abelian group by any nice class you might think of. This transformation preserves a lot of things. Right? So for example, Percy Diaconis, he likes representation theory a lot. So he keeps saying that cutoff is about looking at the multiplicity of the first non-trivial eigenvalue of T. Okay, that's what drives cutoff according to him, because in many examples where you do representation theory on groups, that's actually the case. Well, this transformation here preserves all the eigenvectors of your Markov chain. So in particular, and the eigenvalues are just scaled, right, in a very simple way. So the multiplicities are preserved. So it means that you will have counterexample to this conjecture that multiplicity drives cutoff. There are chains that satisfy cutoff and others that do not, and they have the same eigenvectors, same eigenvalues roughly, same multiplicities. Right? So you can essentially destroy any conjecture that someone makes about cutoff by this by this this transformation.
So such cutoff is nothing has to do with spectral properties.
Yeah, but it's much more than spectral. You know, there are many nice properties of Markov chain. A Markov chain is nice according to people. It's not the same meaning. Nice. Right? For example, you know, personally, I like looking at chains that are monotone. Right? Monotone chains are much better. This preserves monotonicity. So it's just, I like chains that have non-negative curvature. This preserves non-negative curvature. So basically, any structural property you might think of is preserved by this, except for one, which I will mention later. So no, it's really bad news in the sense that, you know, this matrix theta tends to 0, so this matrix is very close to the original one, right? Not only entry-wise, but in terms of all structure you can think of. And yet, one satisfies cutoff, the other does not. So if you come with a theory about cutoff, it will have to be subtle enough to distinguish between those two models. Right? The product condition is not subtle enough to distinguish between those two models. Yes?
With this perturbation, does the time over is in the product condition, does it tend to infinity at the same speed as the original model?
Slightly less the speed, but arbitrarily close to the original. We'll see in the, yeah. Okay, I'm going to prove it so you will see everything. But really, yeah, so the take-home message is that if you want to repair the product condition, you will have to come up with a criterion that is subtle enough to be able to distinguish between those two models, which are very close to each other. Now, just as a spoiler, there is one aspect in which those two models are very, very different. And this is sparsity, right? So in a reasonable model, say random walk on a bounded degree graph or something like that, in many reasonable models, you only do local moves, right? You cannot move from any x to any y. You just move to your neighbors, your immediate neighbors. Right? There is a local geometry. That's what a reasonable model looks like. Okay, but now, you know, in this modification, with a very small probability, but still positive, you are allowed to go from anywhere to anywhere. So in terms of the graph of your Markov chain, right, the graph means, you know, the vertices are your states, and you put an arrow if you are allowed to go from x to y in one step, then the graph is the complete graph here. Right? So this is one aspect in which those two models are very different. So maybe if you want to repair this conjecture by Yuval Perez, you should add something about the sparsity of the model. Maybe reasonable means sparse, in a sense. That would be a way to avoid these pathologies. So this is not enough, unfortunately. So there are examples of, you know, random walk on graph of degree 3, which are expanders. So I don't want to go into the definition, but so those graphs satisfy the product condition in a trivial way, and yet they do not satisfy cutoff. Right? So it's still not about sparsity.
If you think about concentration, could be something like every move has a small impact on the trajectory? Because in this case, we have a move which has a very large...
So I agree, and in a sense, so what we'll see is that the correct assumption is about curvature, and curvature in a sense tells you that, you know, if at some point you make a move, and if you decide to change your mind and make another move, then in terms of where you end up in the end, it will not affect too much this. That's curvature. That's the idea behind curvature, and that's in. Yes, exactly. But still, it's not enough. Remember that curvature, you know, this perturbation preserves this property of each move having a small impact.
Well, not if you choose that move, no? There is a move which has a very large impact in some sense.
Okay, but in...
I mean, not in the sense.
Yeah, in terms of this, it even helps, you see, because, you know, if you take this move, then you are really, in the end, it really did not matter what you did in the past because you end up at the same place. So it even helps, and yet it's not enough. But you are right in the sense that, you know, by putting curvature plus sparsity, then you have cutoff. Okay. So that will be the goal of the lecture. Okay. So let me prove this. I mean, give you a very short proof. It's not difficult once you realize this. So it's a very interesting counterexample in terms of conceptual output, but it's very simple in terms of proof. So, you know, remember that I'm working in continuous time. So rather than saying whenever my clock rings, I flip a coin and decide whether I do this or this. I can think of those as two independent Poisson clocks, one that rings at rate 1 minus theta and one that rings at rate theta, and they are independent. And so just from this, you immediately get that the chance to be at y after time t, there are two cases. Either you were lucky enough to get one magic transition or not. Right? If you were not, right? If this clock here never rung, right? And this happened with probability exponential of minus theta t, then it's just your original process. Right? So this is the modified one, and this is just the original one. Except that you are looking at a slightly slower scale, because now this clock rings at rate 1 minus theta instead of 1. Okay. On the other hand, if you are lucky enough so that one of those that this magic clock rings, then you are at equilibrium, and this will be preserved afterward. Pi of y. Okay, so now you can subtract pi of y on both sides, and what you get is that. It's just this. Okay, and now you take positive parts on both sides. Sum over all y, then take a maximum over all x, and then you get total variation distance for this is exactly total variation distance for your original model, like that. Okay. Okay, so from this you immediately deduce also, remember that the spectral gap is all about how this behaves as t tends to infinity, right? So you know that this, by definition, this as t tends to infinity is just exponential of minus the spectral gap of your modified chain times t plus little o of t. Okay, and so same here, right? This is exponential of minus lambda t 1 minus theta t plus little o of t, and so you can identify and you get that lambda tilde is just 1 minus theta lambda plus theta. So you get an explicit expression for total variation distance and also for spectral gap in both cases. Okay, so from this you can deduce already that you have this result just because now you take asymptotic as n tends to infinity. Everything was for every n. Now I take n to infinity. And in particular, what you see from this formula here is that your modified model, if you look at it at rate at times which are like theta divided by tn, t divided by tn, so times that are of order 1 over theta n, then you see this will converge nicely to exponential of minus t, and this will converge to 1 because we chose the time to be before the cutoff time. Right, so we're looking at times that are of order 1 over theta n, and 1 over theta n is much before the mixing time. So this term is still 1. And this term just gives you the exponential. Right, so this already tells you that the mixing time of your model is really 1 over theta n. And the dependency in the precision is just, how large you should choose t so that this is epsilon. Right? So that this is very much dependent on epsilon, so you don't have cutoff. You have this nice exponential shape in the limit. Okay, so no cutoff. But then in terms of product condition, now if you look at this divided by this, well, this one is like 1 over theta n. That's what this shows. And this one, because of this and our choice, the condition here, tells you that right, in the regime I'm looking at, this is the same as this. Right? The perturbation doesn't see the difference. So in the end, you get just this. TRL is the same for the original model and the modified one. And because we choose theta n like that, this still tends to infinity. Right? And you see, I don't remember who asked the question, but you see that the ratio between the two, you can make it as large as you want by just choosing this theta n as close as you want to this. Okay, so that's a proof of this nice perturbation example, counter example.
How can you react to spectral gap
the spectral gap is a very continuous quantity, right? In the sense that if you perturb your Markov chain by something that has small probability, your spectral gap will be very close to the original one. So you see here in this equation, spectral gap remains essentially the same. Right? It's a very robust quantity. The cutoff phenomenon is not robust in the sense that if you had very rare event, but they destroy cutoff, for spectral gap, this is very robust. Okay. Okay, so finally, I want to present a few important open problems. So discuss a few particular models where cutoff is expected. The main problem is, build a general theory of cutoff, but this is probably too hard. So let me give you a few emblematic problems that the community is working on. So those are examples where we know that the product condition is satisfied. Everyone believes that there is cutoff, but we cannot conclude because of those counterexamples of Igor Pag. We cannot conclude. Right? So let me discuss a few important models. Right. So if you could understand cutoff for any of those models, that would be already a big success, a big achievement. Okay, so the first thing that you could do is maybe, this is too hard, so let's focus on nice chains. Nice means reversible. Okay, so I want to discuss reversibility a bit. Most of the models you would consider are reversible, so it's an important assumption. So let me recall maybe what reversibility is and why is it so nice to have this property. Right, so in general, T is a transition matrix, but you can view it as an operator. It's a nice operator on a nice Hilbert space. My Hilbert space will be L2, and when I write L2, it means L2 of my state space with the stationary measure. It's the right choice for this, as you will see. Right? So this is a nice Hilbert space. You have a nice operator on this. And this operator just acts by multiplication as you would think. Right? So Tf of x is sum over all y, Txy f1. Right? So any matrix is just an operator, right, on functions. Okay. The nice thing is that now that you have an operator on a Hilbert space, you can consider its adjoint. Right? T as an adjoint. T star. So what is this adjoint? Right, the abstract definition is as follows. So the way you define T star is just by duality. So you want this property to be satisfied for every test function f and g. Okay, so you can define it for any operator on any Hilbert space. So that's the general definition. But if you look carefully at what it gives on our very simple setup, what you get is this. Shall we leave or?
No, so VD is not ready.
Okay. So if you take f to be indicator of the state x, and g to be indicator of the state y, you get an explicit expression for the coefficient of this matrix. So t star of x, y. So t star is essentially the transpose of t. So it would be exactly the transpose if your measure was uniform. In general, the measure is not uniform, so you have to pay a small price, which is this. Okay? It's very explicit. And here is the nice news. You see, this adjoint definition is something that has nothing to do with Markov chains. But the nice thing is that when you apply it to a transition matrix, what you get here is a transition matrix. Right? You sum over all this, and by stationarity, pi t, remember pi times t is equal to pi. So that's why it was interesting to look at this particular measure on your state space. Right? So you get the transition matrix when you do this abstract duality, and also so it's also if t is irreducible, then this is irreducible just because if you look at the diagram of your chain, you are just reversing the arrow, all arrows, the direction of the arrows. Right? So if your graph was connected, it still remains connected in the other direction. Okay. So it's still irreducible, so it has a unique invariant measure, and it turns out that this invariant measure is just pi. Right? You can just check that. So T star is an irreducible transition matrix with the same stationary measure. Okay, so you give me any Markov chain, any model that you think of, and there is a dual model which has the same stationary measure. It should play an important role, and you will see that it plays an important role when you want to analyze your semigroup. But you probably know that this has a nice intuitive interpretation, this duality. It's like letting the time go backwards. So let me remind this just as an exercise. It's time reversal. So you can interpret this duality moving from t to t star as just reversing the arrow of time. Inversion. So the exercise is that if you take a Markov process with transition t, and you start from stationarity, so x0 distributed according to pi, and now you compare it to the dual version, which is you look at another Markov process, which is just transition t star, also starting from stationarity. Then there is this miracle that you look at this process. This process, this dual process, is exactly the same in distribution as your original process, but viewed backward in time. So maybe, right? So it's really what you do when you apply this abstract definition of adjoint. When you do this on a Markov chain, it's really looking at your process backward in time. Okay? Yes. No, it's even more than that. It's really as processes. It's easy to see. Right? Yeah. Okay, I'm not going to use that, but you know, there is an intuition behind this this duality, which I wanted to mention. Okay, so now coming back to the general formulation, why is it interesting to introduce this adjoint? You know, in operator theory, when you have an operator which is equal to its adjoint, then many things works very nicely, and that's the same for Markov chains. Right? Definition. So the chain is reversible if T star is equal to T. Okay, so it just means that your operator is self-adjoint, which is generally good news. Right? But in Markov chain, it's just this. And if you apply this definition here, this is the same as saying that for every xy in your state space, you get this detailed balance equation. Okay. Okay, so some Markov chains do not satisfy this, but many of them, as you will see, many of the models you can think of, they have this nice property. By the way, this property actually implies stationarity, right? If you sum this identity over all y, here you will get pi of x, and so you will see that this will pi t will be equal to pi. Okay. So this equation can be viewed as a local version of the stationary equation. So it's a stronger version. It holds locally along every edge instead of globally when you sum over all possible edges. So it's a powerful form of stationarity. But again, in terms of operation theoretical language, this is just self-adjointness. So in particular, when you have a self-adjoint operator, you have nice spectral property. So the eigenvalues of T are real. So I can order them. And I told you that the largest one is always 1. You have as many as the number of states. It's at least -1. Okay, and you have an orthonormal basis of eigenvectors. So I'm going to denote them phi 1. Phi n, right? Each corresponds to the corresponding lambda. This phi 1 is the eigenvalue corresponding to 1, and you can always take it to be the constant function equal to 1. Okay, so this is very nice for studying mixing types. The reason is that when you diagonalize T, right, so what it means is that you take any f in L2, you can project it on your orthonormal basis. Right, this is basic linear algebra. The coefficients are just the projection according to your scalar product. And then you can apply T. And by linearity, you will just get this. So you get T phi I, but T phi I is just lambda I phi I because it's an eigenvector. And you can iterate this. For any n. And then you can divide by n factorial and sum everything. And what you get is that your semi-group PT you can also get a nice expression for it. And you just get exponential of -1, maybe minus gamma IT. And this gamma is just 1 minus lambda. Okay. There is still phi I, sorry. And this is just 1 minus lambda I. Right? Okay, and so in particular, if you take F to be Dirac mass at Y, or indicator of the state Y, and you evaluate this equality, this is an identity between two vectors, so you evaluate it at the point X. And what you get is this nice expression for your for the distribution at time t starting from X. Maybe I'm going to normalize just like this. And then what you get is this nice expression. Okay, so it's an explicit expression, at least if you have access to all the eigenvalues and eigenvectors of the Markov chain, it's an explicit expression for the distribution at time t. Remember, in our toy model, the hypercube, we had a nice explicit expression for this. If your chain is reversible, and if you know a bit of its eigenstructure, you can also explicitate this and hope to do computations and prove cutoff. Okay, so this can be done particularly well on nice groups where you can do Fourier analysis. Okay, the nice thing I want to mention is that the first term, if you look at I is equal to 1, this is just, so gamma 1 is 0. Okay? And phi 1 is 1. So what you get is that this is just 1, plus whatever remains. And you see that if you take t large here, right? So this is like, 1 is the being mixed, being at equilibrium, but then you have an error term that goes to 0 with t. And this error term behaves, the dominant contribution comes from the second largest eigenvalue, right? So it's like this. And this is what we saw in the spectral gap formulation. We saw that, asymptotically as t tends to infinity, what you see is the difference between the two largest eigenvalues. Well, gamma 2 is just 1 minus lambda 2, so it's really lambda 1 minus lambda 2. So that's a special case where you get it very easily. Okay, so in particular, so this formula is the starting point of a lot of explicit, nice explicit bonds on the mixing times of reversible chains. So for many reasons, this in particular, reversible models are nicer to analyze. And if you could solve the question of the cutoff phenomenon for those models, it would be already amazing. Okay, so in many cases, I will restrict myself to reversible chains. Okay, maybe a few other models. I don't have time to say much, but one interesting case of reversible chain is simple random walk on graphs. Right, so you take G, a finite graph, undirected graph, and then you look at this transition matrix. Txy is 1 over the degree if x and y are neighbors, and 0 else. Right? That's one of the most important classes of Markov chain, and this is always reversible. Right? You can check that pi of x is proportional to the degree. It's clear that it satisfies the reversibility. Okay, so that's an important class. And again, if you could understand cutoff at least for simple random walk on graphs, what's the geometry, what geometric property of the graph ensures cutoff? We are very far from understanding this. So we can be a bit more restrictive and look at nice graphs, graphs that are symmetric. So many times we use in our model, we use the fact that there was a symmetry. So we can formalize this by looking at Cayley graphs of groups. Cayley graph is the special case of this where,
The graph that it has to be connected.
right, take a connected graph, yes. So take a finite group and let S be any set that generates the group. Generating set. Symmetric means that if you take the inverse, it's also in S. And then look at this graph. Cayley graph of X S. It's the graph where V is X and the edge set, the sets in your graph, the edges in your graph are all the neighbors of a point X are all the points that you can obtain by multiplying X by an element from S. Right, so you take every point, every element in your group, and any element in your generating set, and that's your edges. Okay, so if you think about it, this cycle example is a Cayley graph, and the hypercube example is also Cayley graph. So in fact, we were looking at those very simple examples where you actually have a random walk on a nice Cayley graph. And there it's easy to see that you have this symmetry, right? The graph looks the same from every point because you can transpose your group, you can move your group elements from any place to any place by applying a simple multiplication. And so all of those are symmetric, very symmetric graphs. Right? So maybe the graph looks the same from every point. Can we discuss that later? Okay, and so finally to conclude this list of interesting examples. So again, if you want to understand cutoff on graph, this is too hard. Focus on Cayley graphs, they are nicer. Still too hard. Focus on Cayley graph of abelian groups. Cayley graph of abelian group. When you do a random walk on that, all you have to care about, the order of the elements do not matter. It's abelian. So all you have to take care of is how many times you use each generator. So it's a very simple process. You can do Fourier analysis, you can do basically everything. Still, our two toy examples are examples in this class. There is no general cutoff criterion for random walks on Cayley graphs of abelian groups. It's still unclear. Okay? And the reason, again, is that you can destroy any criterion by this perturbation argument that I told you. Okay, and last thing, maybe because I mentioned it a lot, MCMCs. So, in Monte Carlo Markov chain, you start from a target distribution, which is very difficult, which is, high dimensional. So high dimensional for me will be like, to keep things simple, you can do more general, but let's look at this. Think of very sophisticated measure like the Ising model, maybe. And then you want to produce sample from pi, so you look at from close to pi, you simply run a Markov chain with pi being stationary. And you run it for sufficiently long so that you have your distribution is close to pi, and that's actually a way to produce samples from the complicated distribution. So there are a few examples. Here are the more important. So I'm going to write the generator for one. So there are many chains that have pi as a stationary measure, but an interesting class is chains that you can put in this form. So the only move that you are allowed to do in this Markov chain is you flip a coordinate, right? So whenever your clock rings, just like for the hypercube, you just flip the ith coordinate. So you replace x by xi, where xi is just you flip the sign of x at the coordinate I. Okay. Of course, if you do this, then it will not be stationary for pi; it will be stationary for the uniform measure. Right? This is the hypercube. This is random walk on the hypercube. So you have to choose the rates here so that they take into account pi. So we'll take a general function of pi of x and pi of xi, right? And we want this to be reversible. So if you want this to be reversible, you want that u times p uv. So your function p should satisfy this, v times p vu. Okay, and now I'm just going to finish by giving you 3 examples of p that are particularly useful in practice. So PUV is just V over U plus V is a choice that works, and this is called Glauber dynamics. I'm sure you have heard. Another useful choice that many people use in practice in Monte Carlo Markov chain is metropolis, and metropolis is just one minimum with V over U. You can check that it satisfies this reversibility condition. So this is metropolis. Okay. And the last choice, which is, I don't know the name for it, maybe you know, it's just this. This also satisfies this. The nice thing with all of those choices are that they are all functions not really of U and V, because remember we started with a problem of trying to sample from a complicated distribution, so pi is difficult to compute, but those are only functions of V over U. So when you apply this, you don't need to compute pi, but you just need to compute pi of x divided by pi of xi. And this is something that is completely explicit for the Ising model or for any spin system that you can think of. This ratio is very simple to estimate. You don't need to estimate pi itself, which is complicated, just the ratio of neighboring pi's, and this is easy. Okay?
So you can see the expectation function.
Yes, exactly. You don't need to compute the constant, the normalizing constant, which would be awful. So it's really an efficient way to sample from complicated model, in particular spin systems. Okay. Maybe, I cannot resist, but even though I hate those, you can also look at diffusion if you want. So this is an important model. So take your favorite potential and you can look at this. All of those examples, they are reversible models, right? You can prove cutoff, a general criterion for cutoff for those classes. For any of those classes, it would be already it would be a huge achievement. Okay. So that's it.